Okay, so I'm going to do a really quick tutorial about Lewis dot structures. And Lewis dot structures are just representations of what kind of covalent bonds are going to look like if they were just dealing with their valence electrons, which is all we really care about at the IBSL level. So the way that we start drawing Lewis dot structures is by counting the number of valence electrons. So the valence electrons can be found by looking at the column number. So for example, nitrogen would have 5 valence electrons because it's in column 5. Oxygen would have 6, etc., etc. Okay? So if I'm looking at something that's actually really simple, and I'm looking at something like H2, H2 brings 2 electrons to the party. So each hydrogen will bring 1 valence electron. There are 2 hydrogens, so I have 2 valence electrons to work with. When I put them together to draw a diagram, I'm actually going to draw them right next to each other, and then I'm going to draw a line. Okay? The line represents a bonding pair of electrons. Okay? Hydrogen only needs 2 because of the duet rule to be happy. So at this point, hydrogen's a pretty happy molecule. We can actually step up our game a little bit by writing something, for example, like HF. HF now adds on a second level by adding a different atom. Hydrogen, however, still pulls in 1 valence electron. There's only 1 hydrogen inside HF, so I'm going to say that hydrogen brings a total of 1. Fluorine, because it's in column 7, has 7 valence electrons, and there's 1 of them, so I'm going to have a total of 7 coming from fluorine. If I add them together, I have a total of 8 valence electrons. Get my pen to work here. So if I have 8 valence electrons total, I have 8 to share between the H and the F. So if I write the H here and the F here, and I combine them together, this is 2 electrons. However, if I look over here, there's still 8 minus 2, or 6 left. Fluorine doesn't follow the duet rule, but follows the octet rule. And the octet rule says that they want 8 valence electrons. So right now, fluorine technically is in possession of 2, because there's 2 that it's sharing with hydrogen. So what I'm going to do now is represent the remaining 6 electrons by drawing dots all the way around fluorine. These are what we call lone pairs. And they always need to be drawn together. So those are lone pairs of electrons. And that actually would be a completed Lewis dot structure for HF. So we're going to do another examples just so you can see how they work. So another good example that we usually use is something like CH4. So carbon brings 4 valence electrons to the party, and there's 1 of them. So that brings 4. H is going to bring 1 valence electron, but there's 4 H's, so there's going to be a total of 4 coming from hydrogen. If I add the 2 of these together, I'm going to get 8 valence electrons. So carbon is actually an interesting atom in that it only has 4 valence electrons, so it doesn't really know if it wants to gain or lose, so most of the time you'll see it in a covalent bond. In this case, it's covalently bonded to hydrogen. It's actually bonded 4 times to 4 different hydrogens. So I'm going to actually combine those 4 hydrogens together with carbon. Again, each line represents 2 electrons. These 2 electrons actually in total, because I have 1, 2, 3, and 4, I actually take care of all of my 8 electrons just by bonding it together. So although it's kind of simple, my final Lewis dot structure would actually only look like this. A similar, in addition to that, is something that looks like this. So this is CCl4. Okay, so C, again, brings in 4 valence electrons. There's only 1 of them, so 4. Cl is in column 7, so it has 7 valence electrons. There's 4 of them. 7 times 4 is 28. This is a total of 32. So it looks a little intense, got a lot of valence electrons. But if I actually go ahead and just bond them all together, I'm going to use 8 of these electrons. And that's going to leave me with, let's see, 24 electrons remaining. So if we look at this, carbon right now fulfills the octet rule because it's sharing 8 electrons with its chlorines. However, each individual chlorine right now only has 2. Okay, so chlorine needs 8 to be happy. So we're actually going to give each chlorine 6. Because there's 24, 6 times 4 is 24, I can actually evenly distribute all of those pieces. So it's not really a problem to do that. So I'm going to go ahead and draw in the 6 dots around chlorine. Okay. So now I have 6 dots around each chlorine, which fulfills the octet rule for that. So if you've got enough electrons to evenly distribute them to all of them, you can actually do so. The next example we're going to do is we're going to do N, let's see if I can get my stylus to work, being very finicky today. So we're going to do NH3. So nitrogen is in column 5, there's 1 of them. Hydrogen brings 1 valence electron, and there's 3 of them. So I'm going to end up with, again, a total of 8 valence electrons. That doesn't happen every time, but it's pretty common in smaller molecules. So I'm going to put nitrogen with all the hydrogens around it. The reason that I surround things with hydrogen is because hydrogen's not going to bond more than 1 time. It's only going to make a single bond. So I can never really put something that looks like this on a structure because this is just never going to happen. So that's why I'm putting them all around nitrogen. So by bonding to nitrogen, I'm going to use 6 electrons, leaving me with 2. Each hydrogen fulfills the duet rule, but unfortunately the nitrogen only has 6 electrons, so 2, 4, and 6. So what I can do is I can take those 2 extra electrons and put them on the nitrogen, and I end up having my full 8, which fulfills the octet rule for nitrogen. So these are all examples of when I have enough electrons to go around. There are examples, however, where there are not enough electrons. So now we're going to look at CO2. CO2 is a pretty good example of a molecule that ends up actually having to share electrons because we run out. So this is CO2. So carbon comes in with 4 valence electrons, and there's 1. Oxygen comes in with 6, and there's 2 oxygens there. I know it doesn't look like it right now. So I have 4 here, and I have 12 here, for a total of 16 valence electrons that I have to play with. So we can already kind of tell with 3 atoms and each of them needing 8 valence electrons that we're running a little low. So carbon, as usual, actually sits in the middle. And the reason that it sits in the middle is because that's really one of the most common places for it to be. It likes to bond with a variety of different things. So I'm actually going to rewrite this for you real quick. So we know that we have a total of 16 valence electrons. So carbon's in the middle, singly bonded to oxygen over here, and singly bonded to oxygen over here. So that's going to take care of 4 of our valence electrons, leaving us with 12. So we already know that this will evenly divide electrons on either side of the oxygen. So if I did that as an example, that's nice. Both of my oxygens fulfill the octet rule. The problem is that carbon doesn't. So what I'm actually going to have to do is take 2 of these pairs of electrons and distribute them. So carbon is now going to be doubly bonded to each oxygen. So it's going to end up looking like this. The reason is because I run out of electrons. So we only make double bonds or triple bonds. We can't make quadruple bonds, but double and triple. Only when you run out of electrons. Okay, so that's the only time you're going to do it. Okay, not that that's most clear, but if you're only going to double and triple bond if you run out of electrons. I think that's probably a pretty good introduction. The only line I want to draw is H2O because it's just really the most classic example of having kind of a Lewis dot structure. So we're going to start with H2 and O. If you want to pause right now and try it yourself, I would suggest that. So H brings in 1 valence electron. There are 2 H's, so I have 2. Oxygen has 6 valence electrons. There's 1 of them, so I have a total of 8. Hydrogen can't bond to itself, so it's going to have to both bond to oxygen. So now that takes care of 4 electrons, leaving me with 4 left. 1, 2, 3, and 4. Each of the individual types of bonds will change the geometry, but that's something that we can talk about later.